I'm Victoria. I'm a PhD student at NUI Galway, and I am also a member of the SIAM student chapter as well. So it's nice to have some other connections. And yeah, today I will talk about Nash Equilibria in certain two-choice multiplayer games played on the ladder graph. This is a joint work with my supervisor, and here are the details in case you are interested. So first, let me give you the main concept about this, which is graphical games. That is different than graph games, okay? So it started back in 2001 with Kearns and other people. So basically, a graphical game is defined by a graph and a game. So the vertices or the nodes represent the players, and the edges or the lines represent the connections between players, and each player will play the defined game with their neighbors, the players connected to them. The main aim is to find the equilibrium configurations and to analyze them somehow. Oh yeah, I forgot to say that you can check the original papers from graphical games. This is not purely theoretical. It has several applications in biology, economics, sociology, computer science. Here I have just listed a few more or less recent papers about those applications, and you can check as well the papers here. So that's it. So for a graphical game, I said we need a graph and a game. So let's start by defining our game. So our game will have two players, 1 and 2, and two choices, A or B. Okay. So in game theory, what we use the concept of the payoff matrix, which looks like this. So what this means is that if player 1 chooses to play strategy A and player 2 chooses A as well, then player 1 and player 2, they both get P. P is just a number, it's a payoff parameters. You can think of it as the number of stars that they get. So if they both choose A, they both get P. If they both choose B, they both get S stars. And if player 1 chooses A and player 2 chooses B, player 1 gets Q and player 2 gets R, okay? And vice versa. So it is a symmetric game. And yes, as I said, those are the payoff parameters, or the number of stars. So those are parameters, but we will assume this relation that R is greater than P and that Q is greater than S. What this means is that we have two Nash equilibrium solutions for this game. What is a Nash equilibrium solution? It is a configuration of strategies in which no player wants to unilaterally deviate from it. So by assuming this relation, we have two for this case, which are here in black, when they choose opposite strategy. Player 1 chooses A and player 2 B, and vice versa. So we have those two Nash Equilibria, which I will shorten by NANE. And we say that this is an anti-coordination game because they must anti-coordinate their responses. Pictorially, we can represent those two solutions in this fashion. For this first solution, player 1 chooses A and player 2 chooses B, and vice versa. So we have here the two solutions. So we are done. We have just defined our game, right? But we need a graph, right? So here's just what I just showed you, those two solutions. And our graph will be the ladder graph, which, remember, the nodes represent players. And in this case, we will have 4K players. So each player will play the defined game pairwise, the game that I just showed here, with all the players connected to them. So for instance, player 4 will play the game with player 3, with player 2, and player 6, and so on for all players. This is our graph, but we will also consider another graph which might seem different, but it's really not, which is the circular ladder. Okay, so as the name suggests, it's just a ladder with matched endings. Here's the matching. So if you take this ladder and you just bend it or draw a line or an edge here, you end up with this circular ladder. Okay, so we have defined the game and the graph. So what do we want? In this case, we want to count the number of Nash equilibria as a function of the number of players. And yeah, every Nash equilibria will look like a string of A's and B's for each player. So that's what we want. So how do we start? Well, for the Nash equilibria in the ladder, to answer this question, first we need to define the best response for each player. Let me be a little bit more specific. So we have here the ladder graph, and let's look at this player specifically. And imagine that the opponents choose to play strategies A, and B. So the question is, what should this player do? Should he or she play A or B? That's what we want to answer with the best response, okay? But it's simple. So just compute the average payoff when playing A and the average payoff when playing B against these particular strategies. And the one that is higher from both of them defines the best response for this player against this particular choice of the opponent's strategies. But remember that we didn't fix the payoff parameters, so those two quantities will depend explicitly on the payoff parameters on R, P, Q, and S. So this is what I just showed you. What does this mean? That we need to make further assumptions on the payoff parameters in addition to the original assumption coming from the two-player game. So those assumptions or inequalities are obtained from those two variables, which are X and Y, which are this difference between the payoff parameters, okay? By definition, they are positive. So we have 4 different cases, which look like this. So for instance, if the payoff parameters, this X and Y, obey this relation, then you have a list for your best response. If they obey this second relation, then you have another list, and so on for the others. First, what is this list? The list of the best response is just having a list of strategies. Like, for instance, if my opponents play A, B, I should play A or B. It depends. So that's the list of the best response. And we have 4. But when you look at the details of those 4 lists, what you find out is that we can recover from this 3rd list. If we interchange strategies A and B, we can move from this list to the 2nd one, the green one, and same for the last list with the 1st one. And remember that we are only interested in counting the number of Nash equilibria, not on listing them. We just want to count. So if you just want to count, interchanging A and B in your Nash equilibrium solutions won't change the result. So what all of this means is that we can focus on analyzing only 2 different cases, those 2, because the result from the other ones will be the same. So the result for this will be the same as for this, and this last one the same as for the first one. Okay, so we have to find the best response, so we can proceed a bit. So we have the payoff parameters that obey this relation, and we have this list, which I didn't show, but it's not important. So we have this list. So what do you do then? Well, you start to build some solutions. So for instance, here I'm showing 3 Nash equilibrium solutions for the ladder with 12 players. 12 players, we have 12 nodes here. And these are Nash equilibrium solutions. As if you recall, that means that every player here doesn't want to unilaterally deviate from it. So this player, for instance, won't change unilaterally to B. He or she is better off with this A. So you start to build some solutions, and these are only 3 for 12 players, but there are actually more. Okay, so when you start playing for a bit, what you realize is that all the solutions that you can build are made of those 4 elementary partial blocks of solutions, which I just numbered as block 0, 1, 2, and 3. Okay, so what this means when you have this with blocks is that this is the picture that I just showed you with the solutions with 12 players, but with our numbering of blocks, we can actually identify each solution by a sequence of numbers depending on the block that you're using. So for instance, that's why the color is there. So for instance, this corresponds to block 0, this corresponds to block 2, and this corresponds to block 1, and so on for all the others. So we can, as I said, identify each solution with a sequence of numbers. Okay, so that's fine. What's the use of that? Well, but that's not it. We have the 4 blocks and this table of the best response. But this table means that there are certain rules to attach the blocks. So you cannot attach the blocks as you please, but there are certain rules that you need to follow. We can think of that or simplify that by thinking of the blocks as having shapes, as, I don't know, these Lego blocks or whatever. So as you can see here, you cannot attach the blocks as you please. They need to fit. So that would represent the rules. And yeah, this block 0 represents this block with 4 players. Okay, so this is just a nice way of seeing this problem. So by using this this numbering or these Lego blocks, here I'm showing one example of one solution for case 1 using k equals to 7 blocks. We have 7 blocks here. That means we have 28 players because each block carries the information for 4 players. So this is a solution, and you can see that the blocks match, so it's a valid solution. And this solution would be identified by the numbering 0, 2, 1, 3, 0, 0, and 2. Okay. So before continuing, let me recap for a bit. So we started with our 2-choice 2-player game with 2 Nash Equilibria and the payoff parameters or the number of stars. And also we defined the ladder graph, and each player will play this game on the ladder graph. And we wanted to count the number of Nash Equilibria as a function of the number of players. So the next step that we did is that to define the best response, this list for the best response, depending on certain inequalities between the payoff parameters, remember X and Y. Then we have 2 different cases when we want to count the number of Nash Equilibria. Effectively, we have 4, but since we are only interested in counting, we can focus on analyzing only 2 of them. So we started with case 1 and found that all the solutions are built out of those 4 elementary blocks of solutions, plus the rules to attach them. And we could think of that as just playing with some Lego blocks or whatever. So what's the use of this? Well, now we have turned the original problem of counting, this numbering, into a combinatoric problem, because now the only thing that we need to do is to count the number of combinations of blocks that are possible given the rules. Okay, so that's our goal now, is to count the number of combinations. So it's kind of a combinatoric problem. So now finally some math is here. So let me denote by this n sub dot j of k. as the number of sequences that end in block J, okay, where J goes from 0 to 3, and it represents the blocks that we were talking about. And K represents the number of blocks used. Remember, from the previous picture, there were seven blocks. So this is just notation. So obviously, the total number of Nash equilibria is the sum, using K blocks, is the sum of all the sequences that end in block 0, in block 1, in block 2, and in block 3, using K blocks. So here is what the picture that I just showed you. Here, K would be seven blocks, 28 players. So yeah, the total number is just adding every possible combination. So now we need to use the rules to attach the blocks. Okay, the rules to attach the blocks. What that allows us is that we can relate the number of sequences of blocks ending in block 0 using K blocks to the number of solutions that end in block 0, in block 1, and in block 3, but with one less block than the original one, and so on for all the others. So effectively, the number of solutions using 7 blocks is related to the number of solutions using 6 and 5, and so on. So when you plug these relations back in here, what you end up is with a recurrence relation, which might be similar to Fibonacci, but it's not. So wait for it. So we end up with this recurrence relation. To solve it, you just try the exponential growth with this R and K as a function of the number of blocks used. This is the general solution where alpha and beta are set by the initial conditions, and the base of the exponential growth is the golden ratio. Okay, so I will spare you the details, but using the initial conditions and working for a bit, then we find a very nice analytical expression to count the number of Nash equilibria for the ladder graph with 4 K players, and it looks like this. Okay, that was for the ladder, but remember that I also mentioned that we could analyze the circular ladder. So for the circular ladder, it's just matching the endings. So we can effectively use the same procedure as before to identify the solutions with a sequence of numbers. So for instance, here we have also 12 players, but you can see that they are matched. So this sequence, this is block 3, that's why this is block 2, and this is block 1. And with this arrow, we denote this part of matching, because the last block should be matched to the first block. So we could reuse our procedure there, but just taking into account that the last block should be matched to the first one. Another subtlety there is that imagine that you have a sequence that starts in block 0 and ends in block 0, that starts in 0 and ends in 1, and 2, and in 3, and with this arrow we denote that it should be a solution for the circular ladder, okay, because we need to match the endings. But this is just an example, but from the rules we cannot attach these two to the left of 0. You can see it here. You cannot bend these solutions because you cannot attach these two to this 0. So we could use the procedure as before, but we need to get rid of those solutions because they are not valid for our circular ladder, because again, you cannot attach them. You cannot attach the last block to the first block. So yeah, we need to count the number of allowed combinations when we match the start and the ending blocks. There are some very ugly details there, but it still can be done. It's a bit tricky, but it still can be done. And finally, after that, you find another very nice analytical solution for counting the number of Nash equilibria for the circular ladder with 4K players. And again, the golden ratio is the star there. Okay, so great, we have found those two. Remember that this was for case 1, right? But we had 2 cases. Well, for case 2, we have another list for the best response. It's different, and this means that we have different blocks. We have, in this case, 6 different blocks and other rules to attach them. But the procedure, it is completely analogous to what we just did. And we find the same recurrence relation. So here, finally, I'm comparing the results. So here I'm plotting the number of Nash equilibria in logarithmic scale as a function of the number of players for the circular ladder and the ladder for case 1 and for case 2. So here are the analytical expressions that we found. So at first glance, when we want to compare those 2 cases, for the ladder, we can see, which are the dots here, we can see that for case 1 and case 2, which is the blue dot here, has always more solutions than case 1. And remember that the case was set by the relation between the payoff parameters. Okay, so there the payoff parameters are having some influence on the result. However, for the circular ladder, that is no longer true, because the number of solutions are basically the same, regardless of the case. You can just check those 2 analytical expressions are basically the same. Okay, so those are our results. So let me just conclude. So for our 2-choice 2-player anti-coordination game and both graphs, first we found an analytical formula to count the number of Nash equilibria, which is very nice because usually you just do an algorithm approach to that, but we didn't. Second, striking result was that the golden ratio was there, totally unexpected. And then, well, the number of solutions for the circular ladder is always greater than for the ladder. I had no intuition about that, but it's maybe surprising as well. And as I said, for the ladder, it changes with the case, which is related to the payoff parameters, but for the circular ladder, it is constant, which might suggest that the topology of the graph is playing the main role there. There are further work and open questions is that we can try to analyze the solutions to compute the total payoff for the society, the social welfare, to see if they are Pareto optimal or not, or instead of the anti-coordination game, let's change to a coordination game, or just try the same but with another regular graph and see what happens, and so on. So yeah, I would like to thank. Here are the details in case you have interest, and I would like to thank all of you and College of Science and the School of Math at NUIG, and I would thank you for listening, and I would happily take any questions that you might have.
Thank you very much. Having on behalf of everyone else who's using emoticons. So any questions for, yes, Erin, let me unmute you. I think now you can unmute yourself.
Hi, this was a really, really interesting talk. I really do love a good bit of graph theory. My question is just, have you thought about changing the model like in slight ways, like maybe rather than turning it into a ladder connecting back on itself in a normal way, just flipping it around and turning it into a Mobius strip? Would that change anything? And also, if you were to generalize it to like the discrete lattice into the integer lattice, like just a grid instead, or turn it into a torus, but I'm not sure. Have you thought about generalizing it to a little bit further than the ladder at all, or does that become too complicated too quickly?
yeah, that's why we started with the ladder. It was less safe. It looked safe, but at the end, you know, there was other stuff. So no, thank you for that. I haven't even thought about the movie strip. Yeah, you're totally right. So yeah, it's very new. I mean, not very new for me specifically. I don't have any idea of graph theory and anything. But yeah, we are trying to maybe, because the circular ladder is a 3-degree graph, so maybe try with a 4-degree to see if our method works or it breaks, because maybe there are no symmetries and the procedure is not good for that situation. But yeah, I will thank you for pointing that out. Yeah.
Cool, thank you. Yeah, so do you think then that that it's the odd degree of the vertices that gives it a nice symmetry? Do you think an even degree would ruin it then?
Yeah, maybe because yeah, for the ladder it's not completely a 3-degree graph, yeah, because of the endings. So that's why it was a little bit more we expected more than that the payoff parameters are all there. But for the ladder, it was completely unexpected, yeah, because it's just adding one edge, and apparently, yeah, for that it works. So yeah, we are trying to think about different degree, 4th degree, like the pentagon, this with the devil, which is a 4-degree graph, and it's a little bit similar. It shares some similarities with the ladder, but let's see, it's a work in progress. Yeah, we haven't done anything yet.
Very cool. Thank you very much.
Thank you.
Lovely talk, and I really liked all of the humor. I couldn't quite find any places to add any jokes into mine.
You will. It's just your was a great talk, but yeah, I'm sure you will find it eventually.
Thank you very much. There is a technical question that I attempted to answer. I don't know if I answered this correctly. Can you go back to where was it? I think it was towards the end of your ladder graph slides.
Let me see. Why is this? Okay.
I think it was about notation.
Maybe here.
Yes. So Joseph was asking, what are you using the dot in sub n? So I said that it represents that the block ends with 0 or 1 or 2 or 3. Is this
yes?
correct?
Yes. What you said is
recursion.
That it ends something that ends in block. Actually, it's J. Yeah.
Right,
but yeah, it is something that is allowed. Okay, a sequence that ends. So this would be like this something of 7 that ends in block 2. So yeah.
Thank you. And I think Joseph actually has a question, so let me unmute him now. Okay. Why can't?
Yes. Hello.
Yeah, okay. Hi. We can hear you.
I was asking about that n, in fact, n sub. So that means 0 is the end of the block.
Yep.
So
yeah,
there is a series of numbers before, which represent the blocks, right?
Yes. So for instance, this sequence here shown would be the sequence of 0, 2, 1, 3, 0, 0, and 2. But with this, we are only counting as I don't care about all of these. I just care about that it ends in 2 in this case.
For example, total number of Nash Equilibria, nk equal n sub, for instance, 2, 1, 3, 0, k then. For instance, the first one, the first term on the right-hand side of the equal.
Here?
Yes.
Yeah, that means just, go on, sorry.
And k equal n sub, for instance, 2, 1, 3, 0, k, example, the first term. For instance, where there is n sub double dot 0, k.
Yeah, this is actually the total number. I don't care if it ends in, because we just want to count. So the total number will be that end in using 7 blocks, for instance, will be the total number of the sequences that end in block 0 using K, that end in block 1, and that end in block 1, in block 2, and in block 3. So it's just like this would be just adding a 1 to this term, because it's just counting last. I don't care.
All the blocks, for instance, end to all the blocks that end in 2.
Yes, all the sequences of blocks that end in 2. Yeah.
Sequences of blocks.
Yeah.
All right.
Because yes, I can see you here. Then if you end in this, then you can attach to form the solution with K equals to 8. You could attach, in this case, block 0 or block 3. So it's just like a tree going up, or the number of solutions. So that's eventually where you get a recurrence relation, because it depending on how many like seeds or starting solutions you start, then you end up with lots
and it
more.
Can be a subsequence of blocks, subsequences of blocks, right?
Yes, you could say that. Yeah, subsequences of
subsequences, not as such the whole space, the whole sequence. That can be a infinite number subsequences of blocks, right?
Yes, because but actually it is finite because there are those rules.
I see.
I don't know if that answers, but yeah, we are just breaking down the total number as the one that ends in 0.
All the subsets that end in 0, for instance.
Yes, following the rules. Following those rules.
Following that rule. All right.
Yeah.
Thank you very much. Sorry to cut in so that we can start the next talk. Thank you very much. That was a very nice talk.